Welcome! Today, we're diving into a fascinating class of materials shaking up the semiconductor world, ferroelectrics. What makes them special? They have a built-in electrical polarization that you can flip back and forth with an external electric field. Think of it like a tiny switchable magnet, but for electricity. For years, materials like perovskites showed promise, but integrating them into standard silicon chip manufacturing, the CMOS process we rely on, was incredibly difficult due to their complex structures. Then came a major breakthrough. Researchers discovered ferroelectricity in thin films of hafnium oxide, or HFO2, especially when doped with elements like silicon or zirconium. Here's the kicker. HFO2 is already a workhorse material in CMOS chips, used as an insulator in transistors. Finding ferroelectricity in a material already compatible with existing factories was huge. These HFO2-based materials work even when incredibly thin, below 10 nanometers, overcoming a major hurdle faced by older ferroelectrics. More recently, another CMOS-friendly option, aluminum scandium nitride, or AlSCN, has also emerged. So what can we do with these improved ferroelectrics? Lots! First, memory. FeRAM, or ferroelectric RAM, uses them for non-volatile storage, data that stays even when the power is off. The new materials allow for smaller, potentially 3D FeRAM designs. Even more exciting are FeFETs, ferroelectric field effect transistors. These merge memory and logic by building the ferroelectric layer right into the transistor's gate. Flipping the polarization changes the transistor's threshold voltage, essentially storing a 0 or 1 within a single transistor. This means fast, low-power, non-volatile memory cells, HFO2 and its relative HZO, are making practical FeFETs possible. There are also ferroelectric tunnel junctions, or FTJs, tiny two-terminal devices, where the polarization controls electrical resistance, creating another type of memory. Beyond memory, ferroelectrics might revolutionize logic itself. The concept of negative capacitance FETs, or NCFETs, uses a unique property of ferroelectrics during switching to potentially create transistors that turn on much more sharply. This could lead to chips that run at significantly lower voltages, saving massive amounts of power. Perhaps one of the most futuristic applications is in neuromorphic computing, building chips inspired by the human brain. FeFETs and FTJs are great candidates for creating artificial synapses and neurons. Their ability to hold multiple stable states, not just 0 or 1, mimics how biological synapses learn and adapt by changing their connection strength. This could lead to highly efficient hardware for artificial intelligence, especially for tasks like pattern recognition. Other uses are emerging too. The high dielectric constant of materials like HZO could boost the performance of standard DRAM memory capacitors. And since ferroelectrics are also piezoelectric, generating voltage under stress, they could be used for integrated sensors or even energy harvesting for small devices. Of course, it's not all smooth sailing. Controlling the exact crystal structure needed for ferroelectricity during manufacturing is tricky. Defects can affect reliability and how long the devices last or retain data. Researchers are working hard to overcome these challenges, improve materials, explore novel options like 2D ferroelectrics, and refine integration techniques. The discovery of CMOS-compatible ferroelectrics, like HFO2, has truly revitalized the field. It opens a direct pathway to integrate powerful new memory, logic, and brain-inspired computing capabilities right onto the standard silicon chips that power our world. Keep an eye on this space. Ferroelectrics are poised to make our electronics smarter, faster, and more efficient.